Welcome, Marquette, and welcome, Jack and Sophia and Roxy and Jacqueline. Thanks for coming. Let's jump right to the quiz. Just a second. There it is. Okay, let's take a look. So what it says is, suppose a study was done to look at the relationship between the percent of county residents who voted for Trump in the last election and the COVID-19 vaccination percent in several counties in the United States. The results of the study are shown below. Okay. And I should let you know, this is one of those, I don't know, maybe because I was interested and I saw some data. I actually did find data and I grabbed some in terms of finding numbers. But I think I'm trying to remember, it might have been New York Times where I found it, somewhere I found it. And it showed those who voted for Trump versus counties percent Trump vote versus counties percent vaccination. And I grabbed some of them. And this is somewhat realistic. Usually I give a disclaimer, but this one's actually a lot more realistic than some of the others I've done. So the question is, find the correlation and explain what it says about the regression line and the scatter plot. All right, so what we need to do is we need to find the correlation. The last thing you want to do is do it by hand. That would be absolutely miserable. I'm actually going to copy these. Notice they're all 2-digit numbers. We'll need that. And then we go over to our calculator. And which calculator to use? Hopefully this is obvious. So what calculator? It was supposed to be easy.
24.
Yeah, it's 24, regression analysis. That's the only calculator we have this week. And so it should be obvious, and it's called regression analysis. Okay, you could do it one point at a time, but I find it easier to just put them in. I copied, I'm going to paste. I'm going to put commas in because that's required. Comma, 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 and comma. And let's do the same for the other. And that is percent Trump voters. And put commas between. Any questions so far? And then I hit plot points. All right. So here's the graph, and we can definitely see what's going on. Hopefully you can see. Okay. And maybe you were surprised, maybe you weren't, but definitely notice that if you have a lot more, if you have a higher percentage of vaccination, you typically have a lower percent of people who voted for Trump in the last election. We can kind of see that. But what we're asked to do is interpret R and interpret R squared. So we look at R, and maybe I'll go 2 decimal places, negative 0.94. So that's the first thing. And again, let's read A again. Find the correlation and explain what it says about the regression line in the scatter plot. So we have part A, and that is R was equal to negative 0.94. rounded to 2 decimal places. So I found the correlation. So it's negative 0.94. So when you have negative 0.94, what does that say about the regression line?
The slope is
It has a negative slope.
Okay, definitely has a negative slope. So that's one thing we can say. The slope of the regression line is negative. Okay. Negative correlation is what R is. So the regression line is about the slope. And remember, the correlation and the slope always have the same sign. And what else can we say? So that's the fact that's negative. What about the fact that it was 0.94? So in particular, very close to -1.
there's a strong correlation, and the tendency, or like if as a percentage of Trump voters increases, there's a tendency that the percentage of people vaccinated decreases.
Yeah, except it's backwards because remember the first variable? The first variable was the percent. I think that's if I remember right. If you look in here at the table, it was percent vaccination is the first and the Trump is the second.
Okay.
Right? So it's that. So we can say the percent of Trump voters, capital, I guess, is very well predicted by knowing the percent of vaccinated people. Any questions on that? So in particular, the regression line is a good fit to the data. Okay, very good fit. It's very close to -1. Any questions on part A? So there's a lot of things you can say. Okay, let's look at part B now. So part B, what it asked for, interpret R squared in the context of the study. So first thing, the calculator gives us R squared. That's easy. You just read it. R squared is about, I like 2 decimal places, 0.88. So let's write that out. All right, so now we need to interpret this R squared. Remember, we want to think of it as percent, and we got to talk about variation or standard deviation you choose. And hopefully you remember how that works is we can say that from county to county, there is a large variation in the percent of voters who voted for Trump. Any questions so far? Okay, but now comes the whole point of the 88%. But if we just look at groups of counties that all have similar vaccinations rates, then this variation on average goes down or is decreased by 88%. Any questions? Any questions on this particular question on the quiz? It's a lot of typing. but you're probably used to that with this class. A lot of words in this class. Okay. Any questions at all? Okay, so that was question 1. Let's go to question 2. Question 2 is a lot faster. I don't know if it's easier for you or not. I can only see if you've got it or not. So for this one, we're supposed to match the scatter plot to its correlation. And we have an A, B, C, and a D, and we have 4 different correlation values. So let's start with A. What can you say about the correlation for this scatter plot, for A's scatter plot?
There's a very strong positive correlation.
Yeah, so in particular, R will be close to what number?
1.
1. Okay, so R will be close to 1, and hopefully you can see this is very close. Okay, they're almost on a line. They're not perfect. Perfect in the real world never happens, for any kind of data collection. So of the 4 choices, which one is close to 1?
0.98.
Yep, 0.98. So I'm going to write A matches with number 4. Any questions on that? Okay, now let's go to B. How about B? What do you notice about the scatter plot for part B?
There's like barely a correlation, not really.
Yeah. I mean, doesn't it look kind of like the night sky? Just a bunch of points all over the place. I don't see any line. Do you? Okay. So that means that it should be close to what number?
0.
0. Okay. And whether it's positive or negative, you really can't tell by looking at it. Being close to 0 just means all over the place. Okay. So which one? 1, 2, 3, or 4?
3.
Yeah, number 3. The only one that's anywhere close to 0. So part B matches with number 3. Let's look at C. Okay, when you look at C, is there correlation positive or negative?
Negative.
Yeah, it's definitely negative because there's definitely a tendency of a decline as you go from left to right. But are they all really close to a line, or they're just visually you can kind of see? What do you think? Or are they somewhat scattered, huh?
Somewhat scattered, so like
Yeah, so you can definitely visually see there's a negative slope, but they're somewhat scattered. And we only have 2 choices left. So of negative 0.71 and negative 1, which one must be C?
0.71 because it's not a perfect line.
Yeah, negative 0.71.
Oh yeah.
Yeah. So number 1. So number 1 matches with C, or C matches with number 1. And I know we could do it by the only one left, but we should look at this. You look at the points on D, and what do you notice about every one of these points?
They're in a perfect line.
Yeah, they are on a perfect line, okay? They're exactly fitting a line. And what's the slope of that line? Is it positive or negative?
Negative.
It's a negative slope. So if it's perfectly on a negatively sloped line, what is always the correlation?
-1.
-1, and that's choice 2 here. So that tells us D matches with 2, which is good because we wouldn't want to make sure they match. I try not to give trick questions with number 2. Any questions at all on this particular question of the quiz? Any questions? So again, this quiz is all about correlation because that's what we did last time. Any questions? Okay, if there aren't any questions, let's go back and go to kind of the week's material. I want to give you a note about something, and I apologize for this, but my office hours tomorrow are going to be shorter than usual. So I got a call, or an email actually, from the other main statistics instructor who needs a sub tomorrow. So there aren't a whole lot of reasons why I miss office hours, but that's one of them. So I'm going to be subbing. So I'm only going to be there in office hours for the first half hour. Okay. Usually you guys don't come on Friday anyway, but if you do, make sure you come at the beginning and not at the end of my office hours. Okay. And in fact, I'm going to actually be in my physical office, which is really weird. I haven't been there in a long time, but my colleague teaches in person on the campus. She's the only one, I think, in California that teaches statistics on campus right now. So I got to be there, and so that's starting. That class starts at 11 o'clock. So that means I got to probably leave my office in about 5 or 10 minutes beforehand. So my office hours are going to be a little shorter than usual, just in case you need help from me. Come in that first half hour of office hours, and then I can help you out if you happen to need it. Okay, but I always like to let you know if something's happening. Okay, probably won't affect most of you at all, but I figure I should mention it. Are there any questions about anything else? Any questions? I don't see y'all jumping in. So while you're thinking, just to let you know, what's happening in 12 days?
That final.
The final exam. So I always like to give you the heads up. So final exam in 12 days. Next week, a week from today, I'll do a full review for the final. So just let you know that it's coming. It's not like tomorrow or anything, but start thinking about it at least. And the final is comprehensive, so you definitely need to be able to do what we've done in class. Any questions before I jump to a major example? All right. So I don't know where you're all from and stuff, but if you're from Tahoe or Tahoe well, what is the most important data that's collected, in my opinion at least, but in a lot of people's opinion? What's the most important data collected in Tahoe? Anyone know? Again, I don't know who's from Tahoe, but and I think snow's important, but not the most important. Yeah, the water in the lake. Okay, so you're probably from Tahoe. Okay, so lake clarity, that is the big thing. And if you're not from Tahoe, if you haven't been to Tahoe, I strongly recommend coming to Tahoe because it is beautiful. And in particular, what we pride ourselves on, besides the snow and the great skiing, but the main thing that we pride ourselves on that nowhere in America is there such a beautiful thing is our lake. And the fact that our lake is beautiful. It's blue, it's clear, and wonderful. And so let me tell you a little story. And believe it or not, I heard it from a statistics student of mine a long time ago, 21 years ago. This is what happened, is that the most important person in all of America came to Tahoe. So 21 years ago, who was the most important person in all of America? And I know if you're 21 years old, then it might be you, but you know. Yeah, President of the United States. Anyone know who that was?
Bush.
No, no.
Clinton.
Yes, Clinton. Okay. Obama wasn't that long ago. Yeah, that was Clinton. And Clinton actually came to Tahoe to a forum about Lake Tahoe to look at how things are going environmentally. And one great thing about Clinton at the time is that he understood statistics. I really think that that should be a requirement of any president is they should all understand statistics because then they get it. And my statistics student actually was there with him. She worked in the restaurant that he ate dinner at, but she got to see this happen. And what happened is they showed him this picture. And this is the depth of clarity data that had happened up to the year 2000, which is 1999, I believe, because it takes a year to finish. So this is a depth of clarity data that was taken. Okay. And just to let you know, because this comes up in our class in a big way, do you think they just look at the lake once each year and call that the depth of clarity? They take a boat down, they look at the lake and say, this is how deep it is?
No.
Nope, that's not what they did. And what I'm going to tell you is going to make you smile. Probably not as much maybe as it made me smile when I heard. By the way, do you know who does Lake Clarity? Do you know who's in charge of the research? Anyone know?
I'm gonna go ahead and take a wild guess and say UC Davis.
Wow, your wild guess was perfect. Yeah,
UC
UC Davis. UC Davis is the one. So I talked to the head of the research department at UC Davis that was looking at our Lake Clarity. And I asked him about it. And he told me, yeah, no, they don't just look at it once. And he guessed how many times they look at the lake? They come in with a boat and they measure, they take a situ disc, which is basically a big white plate. They drop it down until they can't see it. And then they measure the length of the rope when they dropped it down. That's how they do it. And you guess on how many times they do it each year? The hint is it'll make us smile. Oh, all right. Should I tell you? At least 31. So hopefully you all know why they take 31 measurements throughout the year to decide lake clarity. Do you all know?
So they can have an approximately normal distribution.
Exactly. That way they can actually do statistics because if they have a small sample size, then who knows? I mean, assuming you have a normal distribution is silly because it probably isn't. But if you take a sample of size 31 or higher, then you're going to make sure that you have an approximately normal distribution. Okay. By the way, 52 wouldn't work. And those who live in Tahoe understand sometimes we get a whole week of just brutal snow. And that you can't take the boat out. There's safety issues and you're not gonna be able to look, you're not gonna be able to see anything. So those of you who've been here long enough know that there are some weeks like that. So what they do is they go out they try and make it a cloudy day. It turns out it says no reflection. And then they do that at least 31 times. And this is the data that they collected over the many years. Okay, you ready for a trick question? We can imagine the regression line. And is the slope of the regression line positive or negative? Or can we say is the correlation positive or negative? Okay, what you may not have heard is what I said just before that. This is a trick question. Any other guesses? Yeah, it's negative. But the negative is not necessarily because it's getting less clear. I mean, yeah, it's getting less clear, but in terms of seeing it, it has to do with the y-axis. And the y-axis goes down as you go up. So by the way, I would never do this to you on a test, but I wanted to give you a real life example, the most important real life example there is in our area, and that is Lake Clarity. So, so notice that it's 35, 30, 25, 20, 15. We'll go down as we go up, which means everything gets flipped. Does that make sense? Again, that's not a statistics thing. That's just UC Davis's thing. And they wanted to make it look good in terms of the boat and stuff. So it's definitely negative. Does it, what's your guess? What's your guess of R? Yeah, it means the lake was less clear. That definitely means less clear. But what's your guess of R? Let's see if you can guess what R is. I could have given this to you on a quiz. I could have said, what's a good guess of R? And remember, the slope is negative. I wanted to tell you that so you didn't guess, the opposite. Okay, yeah, negative 0.9, that's a pretty good guess because you look at these points, negative 0.88, that's a similar guess. You look at these points, I think there's unquestionably, they gather around a line. Okay, is it perfect? No, but there's no question. You don't have to use your imagination to see a line. Okay, so we definitely can say that R is going to be a negative number, close to -1, not exactly -1. Any questions on that so far? This is kind of a review of what we've already been talking about. And now it's time for the new stuff. So here's a big question I have. And that is, based on this information, what is the best prediction for the lake clarity today? Any questions on the question? Any questions? So you can imagine the president of the United States is in the room, and it was on the North Shore actually, and the UC Davis scientists need to explain to him what's going on. Yeah, x-axis is the year, and it's in the year since 1900. So definitely not the year 65. That was the year 1965. And here, this was the year 1995. Okay, so we can say, what is your best guess for the year? Now, I'm not looking for a number, but we want to think about what we're going to do. Okay, and what we're going to do is we're going to draw or find the equation of the line, the best fitting line. And once we have the equation of the line, then we can plug in the year. Okay, and today, what's the year today, by the way? On the what number would it be on the x-axis for the year today? Wouldn't be 21. 21 would be way over here, way before 1965. So you have to think a little bit deeper, just a little bit. How many years has it been since the year 1900? Not sure where you got 116. How many years has it been since the year 1900? Because that's what the 65 is, a year since 1900. Yeah, 121. So the on the x-axis, it would be 121, which is way over here. It's out here somewhere. And this is all they had at the time. So we're going to guess, we're going to try and find it at the year 121, okay? Or the X value 121, which is the year 2021. Any questions so far? Okay, the next thing we need to do, and hopefully you're used to this, is go to our calculator. So let's do that. And hopefully you all know what calculator number to use. We're almost at the end of the class.
24.
Yeah, 24. So regression analysis. And the last thing I want to do is plot the points one at a time. So I am going to copy and paste the X's that I gave. That I actually typed these out so that I didn't have to waste your time. And then I am going to copy and paste the Y coordinate, which are the meters. And then hit plot points. Okay. By the way, now when we see the scatter plot, now it's not misleading like the other one. Is it clear that we have a negatively sloped line? Yeah, now it should be clear because now the numbers are the way you're used to seeing the numbers. So we really do have a negatively sloped line. That's a good thing. Okay. And again, we can see this line. We can see the scatter plots. We can see that you have a pretty good estimation. And now I can continue on. So by the way, you were pretty close on your R, negative 0.85. So not that far from what you all were guessing. So that means that we have a pretty strong correlation between year and lake clarity. Okay, then we have R squared, which is about 0.72. And we talked about this last time, so I'm not going to type it all out because we did that last time. You were tested on that today. But we can say that, over recorded history, which is since 1965, there's been lake clarity has changed a lot. It goes from, again, looks like around 32 here, and this looks like around 20. That's a pretty big spread of numbers, and they're all over the place. If you just look at the Y values, we have this full spread from 20 to 32, and that's a pretty large correlation, and that's a pretty large spread or a pretty large standard deviation, or there's lots of variation in lake clarity. But if you just focus on areas like 3 years in a row or so, or just a few years together, then there's not that much variation. That variation gets decreased by around 72%.
Wait, what? Correct me if I'm wrong. This isn't a statistics question, but wasn't a lot of the loss of clarity due to some invasive species in the lake? I remember hearing that at some point. I don't know if it's right, but
the loss of clarity was invasive species, but maybe not what you're thinking of. Microscopic invasive species.
that was what I was thinking of.
You were thinking microscopic, okay.
Yeah, because I remember my dad had a boat when I was a kid, and suddenly, like one year, we had to do a bunch of checks.
Yeah.
To make sure that we weren't bringing anything dangerous into the lake. But yeah,
yes.
that's the thing is that there's like a bunch of microscopic invasive species.
Yeah, it's the stuff that causes nitrogen, basically. That's the big problem. And there's some bacteria and stuff that cause a lot of nitrogen, and there's all kinds of problems. So, and some of that's from invasive, some's not invasive, but what happens is as you push more, and I know causes nitrogen, that uses nitrogen. As you push more nitrogen in the lake, then the bacteria and junk grows and survives.
Yeah, no, I know that.
But it's not all invasive. Some is actually not invasive, but if there's not much nitrogen, you don't have that much of it. So it's more of the level of the species, but some of it's invasive too. So it's a mix. Yeah, and I'm not going to get into that because, as you said, it's not stats, but it is cool stuff. And I've talked to, I've lived here a long time, and I've loved science. So I've talked to all the scientists, and it's definitely true that invasive species are a big problem, but bigger problem is nitrogen flow. If you're wondering, nitrates. So that's the biggest problem with lake clarity, and the nitrates cause stuff to grow. and I won't get into the details. But the point is, we definitely have seen that change, and we can. Another way of looking at it is that there's variation in the lake, okay, in terms of clarity. But if you restrict it, if you only look at times that are around the same, that's going to kind of take care of 72% of that variation. Okay. On the other hand, 28%, that's what's left over after the 72%, is from other things. So what do you think, those who are in Tahoe, what are some of the other things that might cause a variation in lake clarity besides human stuff where nitrates are coming in? Because the date is basically the humans. Lots more people coming in and messing with pollution. Anyone know?
Snow or rain?
Yeah. So the next biggie is snow or rain. So this year we should have really good lake clarity, actually, because we're in a drought. So if you have a lot less snow or rain, then you have less runoff. You have less runoff. There's less nitrogen that goes into the lake. So that means that you're likely to have better clarity. Okay. On the other hand, that's only 28% of the variation. The other is us just polluting away. Okay. Just let you know that that's what's going on. Okay. So now we can talk about predictions. I wanted to go through what we did on Tuesday because it is important. And it's, this is a great example of something like that, where you actually, this is true. These are real numbers, by the way. This is UC Davis's numbers and data. Okay. So now comes a big deal. And that's the equation of the regression line. More decimals than we need. So I'm going to copy and paste and then adjust, because we don't really need that many decimals. So the first thing, let me click there. Is let's go to maybe 1 decimal place is probably good enough. 1/10 of a meter, that's good enough. And probably a few decimal places for the slope. Okay. So that's the first thing. And another thing I want to mention is that usually don't use the letter Y. So I'll be honest. I didn't put in the right letter in the calculator because it is brutal to do it online with a program, with a code. So just trust me, the code would have been horrible. I'm not even sure how to do it, but I'm sure it can be done. But the good news is Google, you can do it pretty well. And that is Y hat. So Y with a hat on it is the predicted Y, whereas Y itself is the actual Y. So we say Y hat is equal to 45.6 plus negative 0.25x. Any questions on the equation of the regression line? All right, now I asked you, okay, the question is, based on this information, what's the best prediction for lake clarity today? How do we figure that out? How do we use this new information to come up with the best prediction today? Very simple. That's a hint.
Was X the year?
What's that?
Was X the year?
Yeah, X is a year. Y hat is the lake clarity.
So can't we just put in the current year for the equation?
Mm-hmm. And that's it. Isn't that easy? Okay. I mean, by hand, it'd be a pain in the butt. But the good news is we can just plug in and we can say Y hat. Let's make a hat out of that. So Y hat of 121, because that's, remember, that was our X that we found out, what on the X axis is this year, corresponds to 121 years after 1900, which is now, is equal to 45.6. And then plus minus, I'll write minus 0.25. And then we plug in 121. I'll even put times. Any questions on that? Okay, now we do what I'd rather do, and I'm sure you would too, and that is use a calculator instead of trying to do it by hand. And we get 15.35. I'll do 15.4 is probably good enough. All right. So is that okay? Do you think President Clinton and there were some other major people, there were some senators there also. Do you think they would be okay with the clarity of Lake Tahoe by 2021, by now, being 15.4 meters? So remember, here's the picture. At the time, you know, it was like 25 or so, 26. In 1965, it was like 30-ish. So that means we're talking about a 50% drop in clarity. Okay. And it would keep getting worse. Good. I like your answer. Definitely not. Okay. If you've lived in Tahoe long enough, you know, we're way too proud of our lake. So let me tell you the history of what happened. So this was shown. They did the regression analysis in front of the president. And again, fortunately, the president believes in science and understood it and listened. And so did the senators, and they passed a law, and they funded over $100 million to protect our lake and make this not happen. Okay, so that's the punchline. So this is my opinion for Tahoe, the most important application of regression analysis ever. Okay, and if you don't agree, that's okay, but it was the biggie. And that's why I can forever give this as the example, because it changed our entire, you know, town, okay, and made Tahoe stay clear. Any questions on this example? Yeah, you learned about it in 6th grade. Okay, I was an adult when it happened, but you learned it in 6th grade because I'm older. But yeah, you definitely learned because it was important, but you probably didn't know the details in 6th grade of the regression analysis. And now you do. Any questions on the this big application? Okay, so I'm going to go through again. I'm going to use this as the big application, and then we'll do some more applications. But I want to kind of go through everything, and then we'll just repeat it in the second hour of the lecture. So when you have a line, and we have this line over here, y hat equals 45.6 minus 0.25x or plus negative 0.25x. I'll make that bigger so you can see it better. So when you have such a line, then there are two very important numbers of the line. Let's start out with this one right here, negative 0.25. What is that called in math? What is that number? Yeah. So the slope was negative 0.25. Now, what is a slope in a few words in general? Usually 3 words. Most people remember 3 words.
Rise over run.
Yeah, rise over run. So what I'm going to do is remind you about slope. And I'm going to make this bigger so we can see it better. So the way I like to do it is start out with the word slope, write down what you all learned in, maybe 6th grade, and then adjust until we get true understanding of it with regards to lake clarity and the year. So the slope of a line is the rise or run. That you're supposed to have learned, way back when. So the rise is a change in y. That's what, remember, y is the up down coordinate. So rise means how much up, and that is how much y changed, or how much down. In this case, it's gonna be down. Okay. And then x is the run. Any questions on that? So we can say it's a change in y over the change in x. But we can say one more thing. I'm going to type this out. And that is a slope is equal to, and I know that you probably learned m for the slope, right? Is that what you learned at one point?
Yeah.
Turns out in regression analysis, we usually don't use the letter n. Okay. And the reason is too hard to explain. It has to do with calculus. In fact, I'm kind of teaching it. I taught it yesterday in my calculus class. So just trust me that m is not the best letter for this particular application of slope. And unfortunately, you'll usually see b. And I know b is not what you think of a slope, but there's some hardcore reasons I can't get into. So I tend not to even use a letter because I think that's going to confuse people. So instead, I use the word slope. So the slope was negative 0.25. And what you can always do, because we want to write it as rise over run, you could take any number and make it a fraction. How do you make a number a fraction? Say the number 10. How do I make the number 10 a fraction?
You put it over 1.
Exactly. And you can always do that. So I recommend that you write down the number as a fraction. So negative 0.25 over 1. And I know this is getting small, so let me make it bigger. Any questions on that? Very basic math. And that way, when you see rise over run, you can actually see an over. If you write it as negative 0.25, you're not seeing an over. But if you write it as negative 0.25 over 1, then we see an over. And just to note, sometimes it helps to write this out, or spell it out, I think is a better word. We can say this is a change in y over the change in x. So x changes by 1. Any questions on that? All right, so next we say, what does it mean for x to change by 1? So now let's go into, the application itself. If x changes by 1, what happened? How do you say that in nice, easy words on what does that mean to say x changed by 1? It helps to look what x represents.
A year passed.
Yeah, a year passed, okay? Because that means one more year, because x is the year coordinate. Okay, so what we can say is that for every passing year, okay, so what you want to do is you want to take these numbers and you want to make sense out of them by writing down a sentence that describes the slope. So first thing, if x changes by 1, that means for every passing year. And then we say we predict. So very important, you don't say it will happen. You say we predict that. Now we're talking about a change in y. Now let's go back. What does y represent?
The depth in meters.
Right. Good, the depth of clarity. And instead of saying the depth will increase by negative, that just sounds weird. We predict that the depth of clarity I'm going to write on average because I think it's easier to understand. Will go down, or let's say goes down, because negative is down by 0.25 meters. Any questions on interpreting the slope? Any questions? Okay, so again, the slope, you always want to say as x changes by 1, then the slope tells you how much y is predicted to change. Okay, and then you always write it in terms of whatever you're talking about. You know, don't just write down what I just said and always write exactly the same thing. You have to relate it to whatever you're looking at. Any questions at all on interpreting the slope of this regression line? Okay, by the way, is that a good thing? Is it good that the depth of clarity goes down by, 0.25 meters every year on average? I'm hoping you know that, especially if you live in Tahoe. I don't see it. So what do you think? Is it good that it goes down by 0.25 meters every year?
No.
No, it's a disaster. It's terrible for us. And that's why, again, they looked at this and they said, we can't let this continue. Okay.
Yes, but if you also live in Tahoe, you will know that none of the people visiting care at all. They just care that they can have their vacation and sorry.
Absolutely, but that's why you do. There's things that they did, and they have done a lot of things.
Sorry, I work in tourists. I serve tourists, and it's
no, but a lot of it has to do with construction.
Completely.
Construction and water flow. Yeah, construction and water flow is number one, but I'm not going to get to that because that's not statistics. But I can talk to you after about all the different things that they've done, and because tourists don't even know what they're doing, but there's some things you can do to help. All right, so hopefully you know from your beginning algebra that the slope is an important number, and the other important number for a line is the y-intercept. Okay, do you remember hearing that, I hope? So the y-intercept is the other important number. But I want to let you know that the slope is always relevant when you're having a regression line, when you actually have a correlation. The y-intercept is sometimes not relevant. Okay, so in our case, by the way, what is the y-intercept? I just want to make sure that you're on board, looking for a number. So what is the y-intercept? Just remind
the number or the definition?
The number. We'll get to the definition next, but the number first.
45.6.
45.6. It wasn't a trick question. I just want to make sure that we're all on board. So the y-intercept is 45.6 for this example. Okay. Now comes the definition. So 45.6 is a nice number, but what does it mean? So who remembers what it means to say the y-intercept is 45.6 in general?
At x equals 0, y equals 45.6.
Right. So let's write that down. So at x equals 0, y is equal to 45.6. Okay. And technically, it's actually not y. It's y hat, because y hat is our predicted value. Because the regression line is just a predictor. It doesn't tell you the exact, it doesn't tell you what it really was. It tells us our best prediction. Any questions on that so far? All right, so at x equals 0, y hat was 45.6. All right, so now we want to say, does this even have any meaning? What can we say? X equals 0, what is that now in terms of our particular study?
The like starting point of when they got the data.
Not when they got the data, it turns out. The key is it helps to look at the picture again. Because the starting point was like 1967, I think, or 68, something like that. So what is x equals 0? So notice x equals 68 is right here. That was 1968. What's x equals 0 in this case?
1900.
1900. So it's very important to like look at it and say, what does it mean to even say x equals 0? So the first thing is note x equals 0 refers to the year 1900. Okay, that's just the definition. You know, that's what this line is, how it was created. Any questions on that? Okay, and by the way, I did this. Actually, sorry, I didn't do this one. UC Davis did it, and they chose to call 65 years after 1900. Okay, and I didn't create this. The UC Davis created this. In fact, I don't know if you can see right here, it says UC Davis. It's the UC Davis boat. So again, whoever's doing it is going to make that decision what the x-axis means. And they decided to do it this way because it's visually worked well. Okay, if they let x equals 0 the year 0, it would look very different actually. Because then this 65 would say 1965. This 95 would say 1995. And then x equals 0 would be the year 0, okay, which is ridiculously a long time ago. Okay, but we can talk about 1900. Okay, y hat is 45.6. So we can say, so therefore, our best prediction for the year 1900 is that the lake clarity was 45.6 meters. Okay, there's an issue with this. Anyone know what the issue is? Why this statement actually isn't really valid? So let me read it again, and then I'm going to show you the picture again. So our best prediction for the year 1900 is that the lake clarity was 45.6 meters. What's the problem with saying that? Anyone know? And it's pretty deep. Okay, and by the way, it's kind of a nice pun, just by mistake. So it's pretty deep as in deep clarity, but more importantly, it's deep in terms of thinking about it. Anyone have an idea?
Well, you're saying that it follows that same pattern.
It follows the same pattern, but even more importantly, let me just mention this. If you look at the years where the data is, they're between 1968 or so, maybe 1967 and 1999. Okay. 1900 is nowhere near these points. Okay. And it turns out linear regression is not very good at predicting anything that is very far away from the data. So I'm going to write down the big disclaimer, and this is important. But as a disclaimer, the data values were all far from the year 1900. So this prediction is not trustworthy. So it's very important when someone does regression analysis to understand what you have to worry about. And one of them is that if what you're trying to predict is nowhere near the data values, then you probably don't want to use the equation of the regression line for that. Okay. There's all kinds of historical stuff going on. Pretty much, if you know anything about Lake Tahoe, for example, you know, in the year 1900 and 1940, there was like almost nobody here. So there was nothing going on in Tahoe. Okay. Maybe till 1960. And then that's when things started going bad. And that's because people came. So just to note that this prediction is not a good prediction. So I want to mention a few things. And that is the following. So this is on the y-intercept now. So first, the y-intercept, as we mentioned, is the value of y when x equals 0. Sometimes x equals 0 has no relevance. Okay. So for example, I'm not sure if it was our class or the last class, we looked at your age and how many units you have left to get a degree. Was that you guys, or was that the other section? I forgot which section it was. Does that sound familiar? If not, then it was the other class.
We did something with how many credits, how many units we had.
Okay, it was different. Sorry. The other class did your age and how many more classes you have to take before you get your desired degree. Well, what's the problem with x equals 0?
Well, x age is 0 years.
Right. What were you thinking about when x was 0 for you? Were you thinking about how many classes you had left to take?
No.
No, you were probably thinking about milk and how much it hurt to go through the womb. Because when x equals 0, you were being born. Does that make sense? So a lot of times x equals 0 doesn't really have any relevance at all to the study. And so again, the other section gave that as their example when I had them do one, and that was your age and how many classes you have left. X equals 0 is just silly because no one's thinking about how many classes you have left when you're being born. Is that clear? Okay. I don't remember what I was thinking, but I know it wasn't that. Okay. So again, if x equals 0 has no relevance or is far from the data values, as our example was far from the data values, or if the y-intercept has no relevance, sometimes the value of the y-intercept is meaningless. Okay. And that can happen. So that might be, let's say we did this instead of 0 being the year 1900. Let's say we did the 0 being the year 0. Then you might get a y-intercept of say might get a y-intercept of say 10,000. That would have no relevance because our lake can't be 10,000 meters deep because the mountains, wouldn't even I would say you can't have a lake that's deep because the mountains aren't even that tall. Does that make sense? So sometimes the y-intercept has no relevance, doesn't mean anything. So if any of those happen, then you just say the y-intercept has no relevance. Okay, but if those don't happen, then the y-intercept is the best prediction for y when x equals 0. Any questions on the idea of the y-intercept. Okay, I want to highlight some words, very important, and that is best prediction. It does not mean that we know what y was when x was 0. Okay, even if it has relevance, we don't know it. And that's the difference between y and y hat. Y is the known value, and y hat is the predicted value using the equation of the regression line. Any questions on that idea? Any questions? Okay. And I want to mention this is only going to work if the data actually follows somewhat like the line. So for example, let me remind you of the quiz that we just did. That was this one. Let's say instead of what, our picture, let's say it looked like part B. Then do you think the y-intercept would be useful at all?
No.
No. The line is worthless. Do you think the slope would be useful?
No.
No, nothing's useful. Okay. So if it happens to look like part B, don't do regression analysis. Got it? Okay. You do regression analysis when it looks like part A. Okay. Or obviously it looks like part D. You don't even have to do regression analysis. You have an equation, you're done. Then it's a perfect fit. But more likely you're going to have part A or part C. Part A, you can be very confident about your prediction. Part C, your confidence isn't as that good. Now, we're not going to get into confidence intervals, but you can actually talk about a confidence interval for the prediction. And as you might guess, part A's confidence interval will have a much smaller margin of error than part C's confidence interval, right? Because part C is more spread out. Whereas part B is worthless, so you don't even go there. Any questions on the idea of how regression analysis works? All right, what we're going to do now, since it's 5:03, getting close to 5:04, why don't we take a little break? Come back in about 5 minutes. How about 5:09? And then we'll do more. Okay, welcome back. So hopefully you had a nice little break. Any questions? Any questions before we continue on? All right, let's share my screen again. So we've now talked about understanding R squared, understanding the slope of the regression line, best fitting line, understanding the y-intercept, using a predictive value. So the next thing we have to do is to say, is it even valuable, right? Is it just worthless to do regression analysis, or is it something that is useful? And that is a case-by-case basis. Sometimes it's very helpful to do regression analysis, and sometimes it's not very helpful. As I showed you over here, if it looked like graph B, then don't do regression analysis. It's silly. If it looks like graph A, you definitely want to do it. C, yes, probably okay. Okay, D, we have a perfect line. So again, sometimes you're going to do it, sometimes you're not, but we want to be able to get a little bit deeper than just kind of look at the graph and kind of guess. That's really not the way statistics works. We need to decide go forward or not go forward. So when you think about go forward or not go forward, what should you be thinking about? What tool do we have in statistics that we've been doing the last bunch of weeks?
Hypothesis test.
Exactly. So we want to find out, we want to use a hypothesis test. And most importantly, what we want to do is we want to see, well, is there a correlation between the two variables? If there's a correlation between the two variables, at least the regression line is somewhat helpful. Whereas if there's no correlation, then the regression line is worthless. Any questions on that? So let me show you how the hypothesis test looks. And in fact, I'm going to put this afterwards. So it's always the same. So if I ask you to state the null alternative hypothesis and you know it's coming from chapter 12, you better smile because it's always exactly the same. And it's the first time we've had something that's exactly the same every single example, as long as you're in chapter 12. And that is H naught colon, that you're used to. And you know how to read this next letter?
Rho.
That's rho. I think I mentioned it last time, didn't I? So that's rho. It's a Greek letter. It's not P, and it's not the Greek letter for P either. It's the Greek letter for R, which is rho. Okay, rho equals 0. So the null hypothesis, right? What we don't want to be true, because you don't want the null hypothesis to be true. You're hoping for the alternative hypothesis, is that there's no correlation between the two. In other words, it's totally worthless. Whereas the alternative hypothesis, H1, colon, and that is going to be rho is not equal to 0. And I want to let you know, for the final exam, I promise you that it's only going to be a not equal to. But I'm going to give you a little disclaimer. Sometimes you're interested to show that there's a positive correlation or negative correlation. So there are cases where it could be less than or greater than. And in fact, your homework could have a less than or greater than, but not the exam. The exam is going to be a not equal to. The idea is this a worthwhile endeavor to even look at the correlation and the regression line? Any questions on that? Any questions? All right, so once we have our H naught and H1, we also have our data. what do you always do after you've written H naught and H1 and you have your data? What's the next step? You should be used to this. For weeks, we've been doing this. So what's the next step?
Use the calculator.
Yeah, use the calculator. And the good news is we've already put it into the calculator. So use the calculator means read the calculator. So notice it says hypothesis, H naught, rho equals 0, HA, rho not equal to 0. It turns out that when we're doing regression analysis, there's some very deep mathematics. And the deep mathematics ends up with the same distribution curve as doing a hypothesis test for a mean. And that's that student's t distribution. I don't know if you remember it, but we use that letter t. So the test statistic is going to be a t. Okay, and t is negative 8.73. Is the p-value 9.67 about?
No.
No, why not?
Because it's e to the negative 10.
Yeah, e negative 10, don't ignore that. Okay, it'll be a disaster. First thing, p values are probabilities. Probabilities can never be bigger than 1. So if you ever say p equals 9.7, you have blown it. Got it? P can't be bigger than 1. So you always need to look right a bit until you find it. And it says e negative 10. What does that e negative 10 mean to do? Mean that you should do?
Reject the null.
Yeah, but what is it mathematically? The e negative 10, what does that mean to the number?
Oh, times 10 to the negative 10.
Yeah, so it means move the decimal over 10 places. The first place just moves it to the left of the 9, and the other 9 is going to give you zeros in the decimals. So we have, let's go 967. We can say that the test statistic is equal to, is 8 point something. What was it? Negative 8.73. Okay. And by the way, if you have a z-score or a t-score that's negative 8.73, that is so beyond outlier. Remember, negative 3 is an extreme outlier. Negative 8.73 means that it just couldn't even happen. Okay. It won't happen. That's like almost like chance of a Big Bang happening tomorrow. Not gonna happen. Okay. So our p-value was equal to 0.123456789. And then it was 967. Okay, that's about as small a p-value as you'll ever see. So that tells you that you definitely know there's a correlation. Okay, I want to give you a little warning though. It does not tell you that the correlation is close to -1. It just tells you that we know there's a correlation. So sometimes you'll get a very small p-value because you had a large sample size, even though maybe the correlation might be maybe 0.3 or something. But if you had a giant sample size, that 0.3 is going to be shown. Okay. In this case, we didn't have a giant sample size, so this is one of those that's just clear that we have a decent correlation, strong correlation. Any questions on the test statistic and the p-value? So now the conclusion. And the conclusion is there is strong statistically, and it's strong because we're not just less than 0.05, but we're less than anything you can imagine. Statistically significant. So I'm hoping you're getting this verbiage down, because I try to use the same words every time so you get used to it. Okay, again, there are some other words that are used, but if I change it every week, then I think you'd get confused. So I stick to the same words. So there's strong statistically significant evidence that there is a correlation. Okay, doesn't mean strong correlation, but we know there's a correlation between the year and the lake clarity. Let me make this bigger so you can see it better. Any questions at all on the hypothesis test for correlation?
I did have one question. I'm not sure if you said this, but can it also be greater or less than? Like,
Yeah. And in fact, if you go to the calculator, do you see the greater than or less than?
oh, yeah.
But here's what I said. I don't know if you remember, but this is what I said, is that on the final exam, which again is only in 12 days, I promise you that it'll be a not equal to.
Oh, okay, so it's always going to be the same for what?
Okay, just for the final, because again, I can only do so many details in the class.
Okay.
The class is hard enough that I try to keep it at,
No,
minimum.
yeah, that makes it
But
easier.
yeah, but maybe, in 2 years when you're doing some research, you may have to show you have a negative correlation or a positive correlation, and that's the less than or greater than. Okay, and in fact, the calculator used to not even have the less than or greater than, but I got some complaints from some other instructors from down in Southern California, so I put it in. Okay, so just let you know that it is there for us. Okay, and by the way, it's easy. All you do is you click on it and then hit plot points. Okay, and notice it changes everything. Whereas if I click there and hit plot points, then that changed the number a little bit, but we're here. Any questions? Any more questions? Good question, though. Any other questions? Okay, what I thought we'd do, one thing to note, and this is very important, and when you're doing regression analysis, there are some words that you should never use. One is causes. Okay, you never say that we have a correlation, so increasing this causes that. That's just wrong. Okay, it doesn't mean it doesn't cause. It just means that the statistics doesn't establish cause. So let me give you an example. And this was done probably 90, let's see, like 70 years ago or so. And that is, they were looking at how many cigarettes people smoked and how long people lived. And they had data, and they found out that there was a strong correlation. So in other words, they had an R squared that was very close to 1. And in fact, as you might guess, if you smoke a lot more cigarettes, then lifespan tends to go down. Okay, so R turned out to be, R was negative. So if all you have is the data, the statistics, in other words, you did a study and you just looked at how many cigarettes people smoked a day and when they died, how long they lived. And you did this whole regression analysis, you found a strong correlation. Would it be okay to say that smoking cigarettes causes early death? What do you think? Based on the statistics.
No.
Yeah, it wouldn't be okay. So what happened is they did the statistics, okay? And then of course people say, well, it may not be the cause. So this is very important to note, is that statistics is a piece of research. So once they had that statistics and they saw that there was a correlation, then it's in the hands of the biologists, okay, and the doctors. So then they went in and they did x-rays and they did all kinds of things, and they saw that there was a cause, not because of the statistics, but because of biology and chemistry. So chemistry and biology can establish cause. Statistics does not establish cause, but statistics sends the biologists and chemists to study and to see if there's a cause or not. Any questions on that? So this is so don't ever use the word cause if all you have is statistics. Okay, so I gave you an example where, you know, there is a cause, but statistics didn't do it. Here's another example. Let's say the X variable is how many gray hairs a person has, and the Y variable is their age. Okay, do you think there's a correlation to that?
Yes.
Yeah. If someone has a whole lot more gray hairs, okay, it doesn't mean they're super old, but they're definitely more likely to be old, right? You look at them and say, hey, you look old, right? Does that mean that if, again, I don't see you, but let's suppose you don't have any gray hairs, but let's say tomorrow you went and you dyed your hair gray. Are you suddenly going to get old because you just caused yourself to be old because we had this correlation? What do you think? If you dyed your hair gray, is that going to make you old or cause you to be old? Hopefully you all know.
No.
Definitely not. Okay.
Wouldn't that be a fun alternate universe?
Yeah, it wouldn't be. Yeah, I mean, it may feel silly to do that, but it's not going to make you old. So that's, even though you could have a strong correlation, does not mean you have a causation. So that is a mistake a lot of people make, is that you have to have not just statistics, but also science to establish cause. Okay, and just note the word because. If you look at all but the first two letters, what do you see? It's not a trick question. Yeah, you see cause. So the word because is a bad word to use for regression, because that inherently describes cause. Another one which describes cause is that if you do an if then statement, and in particular, if then it will, that's a cause or a knowing about that it will happen. And you can't say that either. Okay, you can only say if then it is predicted that. So again, regression analysis is about predictions. It's not about matter of fact. We're doing a y hat, we're not doing a y. We're just looking at a prediction. So very important that when you write down the conclusion for regression analysis, that you don't do anything that even remotely sounds like causation. Any questions on this idea? Okay. Sometimes there's causation, sometimes there isn't, but it's not the statistics that's going to make that happen. Or it's not going to statistics that's going to say, yeah, we know. Any questions on these words to avoid? I figured I'd show you the punchline of the Lake Clarity example. So by the way, what happened? What do you think happened again? I told you there was all this money brought in because Clinton understood science and statistics, and then so did the senators, and they put in all kinds of mitigation efforts. Do you think that Lake Clarity is at 15 or so meters now? What do you think?
No.
No. So just let you know that having a prediction does not mean it will happen, because things can change. And the good news is things changed. And again, they put in all this money, they did mitigation factors, they did everything they could to get that nitrogen to stop flowing into the lake. Okay, I won't get into the details of how they did it, but I'll let you know that it happened. And let me show you the picture, which makes me happy. So again, things got bad. And then the law got enacted, the money got funded into stopping Lake Clarity issues. And what do you notice from when things were really bad to now? Did things keep getting worse and worse and worse, like the prediction said?
No, levels out.
Right, levels out. So this is an advertisement of why statistics is important. Because when you have statistics, you can identify issues and then fix them. And once you fix them, now you've changed the mathematics so the disaster won't happen. And this is a great example of the disaster not happening. Notice it's not flat down. It goes up and down and up and down and up and down. Why do you think it does that? We already talked about that.
Snow and rain.
Yeah, snow and rain. Okay. Lake Clarity is very good around here. Do you know what happened around here in 2014? Kind of 2012, 13, 14, 15. Those of you who've been in Tahoe long enough, or California even. Okay, that was that giant drought we had. I don't know if you remember, but we had a big drought in those years. So again, now we're starting to see all the other things that are predictors, okay, of lake clarity change. Okay, but the date is no longer important, because year to year it's not changing anymore, because we're going forward in years. Now it's really weather, and that's what's changing things. So my guess is the next dot is going to be lower because we have a drought this year. Any questions at all on kind of the reality? Okay, let's do another example. Okay, and by the way, I want to do a disclaimer. Unlike the example I just gave you, I made these numbers up. In fact, during that little 5-minute break, I threw some numbers in because I figured we have time for another example. Okay, but this is realistic. And that is, let's look at years of successful education after 10th grade and salary at 30 years old. Okay, and let's suppose a study was done. And we have 6 years of successful education, 2 years, 4 years, etc. There was even a 0-year time. And then we have, and this is in thousands of dollars, 75,000, 18,000, 30,000, 35,000, 100,000, 220,000, etc. So now the question is, perform a full regression analysis. Any questions on the question? Okay. Often you want to do a hypothesis test first. And anyone know why?
To see if it's even like significant.
Yeah, because if you fail to reject, if you don't have any correlation, then it's time to stop. It's time to quit right there. Okay, but if you reject, if you do have a correlation, then you can talk about everything else. But if you don't have evidence that there's any correlation at all, give up. Any questions on that? Okay, so what I'm going to do is to save some time, I'm going to copy and paste. And we've got that. And we've got this one. And we could hit plot points. Okay, what do you notice? Do you think we should continue on, or we should quit and say this is worthless?
Continue.
How come?
Because the p-value is very, very small.
Yeah, the p-value is 0.000116. Okay, so that means that we have statistically significant evidence that there is a correlation between the number of years of education after 10th grade and salary at 30 years old. Okay. And I made these numbers up, but I always try to make things reasonable. And do you agree that you would probably expect a correlation?
Yeah.
Yes.
If you go to college for a lot of years, you're probably more likely to make more money. Whereas if you drop out of high school in 10th grade, you may not make so much money. Does that make sense? Okay, so that's the idea. I tried to make this realistic. So here's what I want to do. Okay, because we got some time. We got everything else, and including the picture. Okay, and here's our picture. Let's see if you can, I'm going to give you about 3 or 4 minutes, or maybe a little longer, perform a full regression analysis. And what I mean by that is, because it's all here for you, calculator did it, interpret R squared, maybe make a prediction. And let's suppose make a prediction for, how about your salary? Make a prediction for, although this may not work if you're too old already. if you're over 30, that you can't talk about it. Okay. But how about, a salary of someone who did the, let's say 4 years of, let's say 5 years of undergraduate work successfully, because on average it takes around 5, especially if you go to community college first, typically 5. And then of course the 2 years of high school, so 6 years. So if you can make a prediction on what the salary for a 30-year-old would be who had 6 years of education after 10th grade. And also interpret the slope and interpret the y-intercept if it's meaningful. And if it's not meaningful, explain why it's not meaningful. Any questions on the task that I'm putting yet? And I want you to spend a few minutes doing that. Okay, and if you have questions, I'm here to help out. But I want to make sure that you give it a shot. There aren't that many of you, so it's just a few of you.
What was after 6 years?
Yeah, 6 years. Sorry, 7. Did I say 6? Yeah, 6 years. So like 4 years of undergraduate education, which is sometimes a bachelor's degree, and also your 2 years of high school after, 10th grade. And I'm going to give you a few minutes to do that. And hopefully you get this, okay? If you were taking good notes of what I was doing on Tuesday and now, you should be able to make it happen, and then we'll go over it. So I'm going to give you a little bit of time to work on it. If you have questions, you can ask. And just a reminder, X was the successful years of education after 10th grade, and Y was salary in thousands of dollars at the age of 30. And I do think it's very important to, instead of just listen to me, to actually try it yourself and then see if you get it right. Okay, so it's a piece of it. There's a lot of things you're doing. One of the things you're doing is you're making a prediction. Another is you're interpreting R. You're interpreting R squared. You're also interpreting the slope and interpreting the y-intercept if it is meaningful. And if it's not, explain why not. So again, if you have any questions, let me know. Okay. That's a possibility, but you don't make a negative salary. This is salary, not bank account.
My dude, I said it was irrelevant.
Yeah, so you're right about that. That's what I'm saying. You're right.
You could have just said I was right.
I did.
No, you didn't.
That's the first thing I said, and then I said and.
You still tried to correct me. My dude, it's right. Move on.
No, I was just reading your answer. That's all. Okay, give you one more minute, and then we'll go over it. Okay, let's go through. I'm just going to go through an order at which we did things. So let's start with R, which is about 0.9. What does that tell us if R is about 0.9? So I'm going to go back here. So if R is 0.9, what can we say about the correlation?
A strong positive correlation.
Yeah, there is a strong positive correlation between education and salary. Any questions on that? Okay, and again, I'm trying to make these reasonable. I made up the numbers, but if I did a real survey, it wouldn't look much different. Okay, now R squared, I like to go 2 decimals because then you can talk percents, is about 82%. Okay, so you're right to say 82% of variance in similar groups, similar to that, but let's go context of the question. So I like to start out by saying there is a large variation in salaries. But if we only look at people who all have the same years of education, then this variation is decreased on average by, and that was 82%. Any questions on this particular explanation? Okay, so we did that. Now let's do the prediction. So how do you make a prediction for someone who has 6 years of education after 10th grade, of successful education? Very simple. And I know we got a 71. Do we have a second on the 71? I don't see y'all jumping in. If you take the x equals 6, I'm just going to do it in my head. 6 times 16 is 96. 96 minus 27 is 69. But if you do the 0.4, 71 sounds right. I can only do so much in my head. So we can say is
myself.
Huh?
I will second myself.
Yeah, our best prediction. I was hoping for others to second you. You got it right. It was awesome. I'm hoping everyone understands it though. Okay, our best prediction for the salary, prediction for the salary of someone with 6 years of successful education after 10th grade is that they will make and that was $71,000 at age 30. Let's look at the slope. So now the slope was about 16. I'm just going to call it 16. and that's 16 over 1. So that tells us that for every additional year a person has of person successful education, after 10th grade, on average, they are predicted to make an additional $16,000. Any questions on the slope? Okay, and then finally the y-intercept was -27. Okay, so by the way, if x is 0, there's no issue with that. That just means you dropped out of high school in 10th grade, at the end of the 10th grade. That can happen. We even had a data value at 0. So there's no issue with that. On the other hand, you can't have a job that pays you negative $27,000 a year. Okay, it doesn't work that way. Jobs don't pay negative money. So since negative 27,000 cannot be a salary, y-intercept has no relevance. Any questions at all on this example? Okay, we're about out of time, so I'm going to stop my share and I'm going to stop the recording.